Welcome everyone to this explainer. Today, we're unpacking the magic, the hidden architecture behind real-time internet interactions. If you've ever wondered how the apps you use every single day seem to just talk to each other instantly, seamlessly, without missing a beat, you're in the exact right place. We're going to demystify the architecture of the modern web. So let's just dive right in.
Picture this. You're building an e-commerce platform. Your customer just hit buy, and you're relying on an external payment processor, like Stripe, to actually collect that money. Once the user pays, your system has a ton of work to do, right? It needs to mark the order as paid, fire off an email invoice, notify the warehouse to pack the box. But here's the massive catch. Stripe operates on its own completely separate infrastructure. You don't control it. So how on earth does your app know instantly when that payment actually succeeds?
Here is our roadmap for the explainer today. We'll start with a polling problem, move to the webhook solution, dissect the anatomy of a request, talk about building a secure receiver, and finally, look at designing for massive scale.
All right, part 1, the polling problem. Let's look at the naive way to handle data updates.
When two systems need to share state, the absolute most basic old-school solution is to just keep asking. Did the payment clear? How about now? Is it done now? That's called polling. Now imagine doing that for every single order on a platform with the traffic of Amazon. It completely falls apart. It's a massive waste of server resources, bandwidth, and time. Instead of your app constantly begging for an update, wouldn't it be better if Stripe could just push the data to you the exact millisecond it succeeds? Well, that is the foundational concept of a webhook.
The real world actually mirrors this perfectly. Think about walking into an insanely busy restaurant. The host tells you, hey, it's a 30-minute wait, leave your number and we'll text you when your table is ready. You don't just stand at the host stand staring at them asking every 2 minutes if your table is ready. You walk away, you get a drink, and when it's your turn, they notify you automatically. That shift from standing around asking to leaving a callback number and waiting to be notified is exactly the shift from polling to the event-driven logic of webhooks.
Which brings us nicely to section 2, the webhook solution.
Let's walk through the actual life of a webhook chronologically using a real-world example like a GitHub pull request. How does your system actually know when someone opens a PR? Step 1 is registration. You go into GitHub, give them your webhook URL, basically handing them your callback number. Step 2, GitHub just quietly monitors its internal event stream. Step 3 is the trigger. A developer opens that PR and boom, GitHub automatically prepares a package of data and shoots an HTTP POST request directly to your URL. Finally, step 4, your server catches that request, verifies it, and kicks off your CI/CD pipeline or pings your Slack channel.
So what exactly is inside that package of data? Let's crack it open in section 3, anatomy of a request.
That HTTP POST request hitting your server has two main parts, the headers and the body. The headers are carrying vital metadata and security info. You've got your content type, the user agent telling you who sent it, the X event type spelling out exactly what happened, like paymentintent.succeeded, and a super important X signature for security. Below that, you have the request body. This is usually just structured JSON data packed with the gritty details of the event itself, the specific order ID, the dollar amount, the user involved, all that good stuff. Now, receiving a POST request sounds incredibly simple, right? But doing it safely in a production environment is a whole different beast. Welcome to Section 4, Building a Secure Receiver. Let's quickly demystify a crucial piece of backend jargon, idempotent. Networks are unpredictable, messy things. Webhook providers will occasionally duplicate, retry, or replay events. If you charge a customer or ship a laptop every single time you get a duplicate ping, you are going to have a very bad time. Your receiver absolutely must be idempotent. That means ensuring that processing the exact same event multiple times has absolutely zero side effects. You do this by checking the unique event ID in the payload against a database of IDs you've already seen, guaranteeing exactly once processing.
On top of that, your dedicated endpoint has to play strictly by the rules of HTTP status codes, just so the provider knows you actually got the message. First, only accept POST requests over a secure HTTPS connection, no exceptions. When you get a good event, hit them back fast with a 200 OK. If the payload they send is totally malformed, return a 400 bad request. And whatever you do, try to avoid 5xx server errors. If a provider sees a 500 error, they just assume you're temporarily down, and they will relentlessly retry sending that same webhook over and over.
Here's the scary part. Webhooks are public endpoints. Literally anyone on the entire internet can try to send data to them. So you have to validate incoming requests by verifying the cryptographic signature,
which is usually an HMAC. Basically, you and the provider set up a shared secret key, like Stripe giving you WSC_ABC123. Stripe uses that secret to cryptographically sign the payload. When your server catches it, you run that exact same math using your secret. If the signatures match up, you know for an absolute fact it really came from Stripe and not some hacker trying to fake a successful payment.
All right, we have a secure receiver. Now let's escalate this to the macro level. Section 5, designing for massive scale. This is the ultimate infrastructure test. Let's say your server processes every step of an order synchronously. It validates the payload, writes to the database, calls 3 other APIs all at once. Suddenly, a marketing campaign goes viral, and you get a massive spike in webhooks. A simple synchronous handler will quickly buckle under that kind of traffic. You'll get timeouts, dropped events, the whole shebang.
To survive, you have to decouple the process. When a webhook hits your server, don't do the heavy lifting right away. Just validate the signature and immediately toss that incoming request into a message queue like Kafka, RabbitMQ, or AWS SQS. Store the raw event in a database for auditing. And then, this is the secret sauce, instantly return that fast 200 OK to the provider. The actual business logic happens later. It gets processed by asynchronous background workers pulling from that queue at their own safe pace. And if a worker fails, it just retries the event with a smart backoff strategy, like exponential delays, so it doesn't crush your downstream services.
But what if an event is just cursed? It keeps failing, no matter how many times your background workers retry it. That's where the dead letter queue comes in. A DL queue is basically a quarantine zone for problematic events. Instead of letting one bad payload eternally clog up your main pipeline, or worse, silently disappear into the void, you route it to the DL queue. From there, your engineering team gets an automated alert, they investigate the root cause, fix the bug, and manually replay the event.
And look, you can't fix what you can't see. Observability is totally non-negotiable at massive scale. You have to be tracking metrics like total webhooks received, processing latency, and most importantly, your queue length. If your queue is growing faster than your workers can drain it, you are falling behind. Tools like Prometheus and Grafana, Datadog, or the ELK stack are lifesavers here. They give you the dashboards and alerts to catch those infrastructure bottlenecks way before your end users ever notice a problem.
So the next time your phone buzzes the exact second your Uber arrives, or a Slack notification pops up the absolute moment a colleague pushes code, I want you to ask yourself, what invisible, massively scalable webhook pipeline just made that happen? We've journeyed all the way from the clunky, resource-heavy days of polling right through to these sleek, decoupled, event-driven architectures. I really hope this explainer left you fascinated by the hidden infrastructure of the real-time web and totally hungry to go build some highly scalable receivers of your own. Thanks so much for diving into this with me today.